Welcome to the Decision Support for Digester Algae Integration for Improved Environmental and Economic Sustainability, or in short, the Dairiees project. Images and references from Environmental Protection Agency, or EPA, the Agriculture and Horticulture Development Board, or AHDB, and Google Images. The INL is working in partnership with the University of Idaho and Boise State University to make this project possible. Let's start with a brief introduction. We live in a beautiful world that has existed for thousands of years, supporting biological life forms like us. Sadly, humans have left their mark on the environment. The issue of global warming has come to our attention. A significant contribution to global warming is greenhouse gas emissions, which are made up primarily of carbon dioxide, also known as CO2, and methane. Several industries and processes contribute to greenhouse gas emissions. Today we're going to focus primarily on industrial processes. Dairy operations constitute approximately 2.5% of annual U.S. greenhouse gas emissions, one of the largest industrial sources of greenhouse gases in the United States. Dairy manure also contains concentrated nutrients of nitrogen and phosphorus, which are harmful to adjacent bodies of water. In January 2009, the Innovation Center for U.S. Dairy announced a voluntary goal to reduce greenhouse gas emissions by 25% in 2020. How is this going to be accomplished? To fully understand the problem, let's examine the current process a majority of dairy operations use. Let's create a hypothetical situation with a dairy owner that owns 500 dairy cows. The cows are well taken care of and their stalls are cleaned of manure twice a day. The manure is mixed with water and stored in large open ponds or lagoons. The mixture is sent out to fields where it is spread as fertilizer. At the end of the day, the dairy owner is happy because the dairy is easy and not very expensive to operate. What they don't realize is that the manure being spread as fertilizer is releasing about 2,600 tons of greenhouse gases per year directly into the atmosphere, increasing odors and causing nutrient overload on fields and adjacent water bodies. The Environmental Protection Agency, or EPA, and the Innovation Center for U.S. Dairy are promoting installation of anaerobic digesters, which can be used to generate electricity. Despite industry support for installing anaerobic digesters, voluntary implementation from dairies has been slow for several reasons. The sale of electricity alone is not enough to make digesters profitable, and this is where Idaho National Laboratory, University of Idaho, and Boise State University join the ballgame. A novel treatment system has been created with a two-stage anaerobic digester that optimizes other sub-processes. Overall, the system creates electricity and additional products with economic value. Let's use the 500-cow dairy owner example again, but this time the new integrated system is implemented. The manure is mixed with water again, but instead of being stored in ponds or lagoon, it is transferred to the first stage of the anaerobic digester known as the fermenter. It is stored at a high temperature for 4 days to allow for increased bacterial reactions. This community of bacteria is called acidogenic bacteria, which is used to create volatile fatty acids, or VFAs. A centrifuge is used to separate the solids from the liquid. The majority of the liquid is transferred to the polyhydroxyalkanoates, or PHA reactor, where PHA compounds are created from the VFAs. The PHA compounds are broken down to make polyhydroxybutyrate covalerates, or PHBVs, which have properties similar to the plastic used in milk jugs. The remaining fluid is sent to the HTL reactor. The HTL reactor uses high temperature and pressure to break biomass down into liquid components, which produce bio-oil and sugars. The remaining liquid and all the solids or manure from the fermenter are fed into the anaerobic digester. Over a period of 10 to 20 days, the anaerobic digester breaks down the manure in the absence of oxygen. This allows bacteria called methanogens to form. Methanogens create biogas that is captured and heads to a generator where electricity is produced. The residual solids are dried and used as animal bedding and agricultural fertilizer, and remaining liquid can be used as fertilizer for soil. So, what does the rest of the liquid from the PHA reactor and the anaerobic digester do? It helps with algae growth. Phototropic microalgae thrive off of nitrogen and phosphorus, CO2, and sunlight. The liquid from the PHA reactor and anaerobic digester is rich in nitrogen and phosphorus nutrients. The algae biomass is harvested and is processed either by HTL or pyrolysis, which is the heating of organic material at high temperature in the absence of oxygen. The products produced are bio-oil, biochar, which is used as fertilizer, and syngas. The remaining liquid and biomass from the HTL or pyrolysis processes are fed back into the fermenter, AD reactor, and algae cultivation in a closed-loop system. How will the dairy owner know if this integrated system would work for them? That's where the Idaho National Laboratory plays a part. An Excel-based model is being designed that will be available to the public in 2016. Users input the number of dairy cows and select several other factors. The input values are sent to a spreadsheet that calculates the revenues and expenses of implementing the integrated system, and the user is able to decide if it's economical for their situation. The model also tells the dairy owner whether the system makes sense from an energy balance point of view, along with the percent reduction of greenhouse gases emitted and nutrients released to the environment as a result of the integrated system. For example, the current model shows the percent reduction in greenhouse gases with the integrated system is 82.7%. Let's summarize what we've learned. The integrated system not only reduces greenhouse gas emissions from dairies, it also produces value-added commodities such as electricity, fertilizer, bedding, bioplastics, and biofuels. The Dairiees model allows users to easily navigate through the complexities of the integrated system to determine their future actions. Hopefully, those actions will result in a healthier environment. This research was funded by USDA NIFA Award number 2012-68002-19952. Data for the fermenter, anaerobic digester, and PHA reactor were provided by Professor Eric Coates of the University of Idaho. Algal cultivation data was provided by Professor Kevin Ferris of Boise State University. The Dairiees model was developed by Rebecca Sisa and Corinne Wendt under the mentorship of Dr. Donna Guillen.